with chapter 3 behind us, we're ready to move on to chapter 4. And we're going to look at a whole new class of functions. Okay, these guys are called exponential functions. And we're going to look at our first one. Okay, let's say f of x equals 2 to the x, right? Rather than having our variable in the base, it's in the exponent. We're going to compare this directly to, say, g of x equals x squared, right? Let's first evaluate this at, we'll say 3, right? Well, 2 to the 3 is 8, okay? And g of 3, right, or 3 squared is 9, right? So our parabola is growing faster than our exponential. But look what happens here, right? If we were to say do f of 10, right? Well, that's 2 to the 10, right? And for those of you who are good with your powers of 2, that's 1024. Versus g of 10, well, that's only 10 squared, or 100. And it's like, okay, well, f has grown a little bit faster. Let's go even bigger, right? Let's look at like g of 30, right? Surely this will be very large, right? 30 squared is 900, okay? But f of 30, well, f of 30 is 2 to the 30, right? Or 1.07 times 10 to the 9, right? That's over 1 billion. These exponentials grow extraordinarily quickly, okay? And that's why that's one of the points that's, interesting us to study them, right? To see how these fast-growing functions behave compared to some of the stuff we've looked at in the past, right? If you go back to, I believe it's lecture 1, we talked about these sorts of laws of exponents. Now would be a good time to actually go back and kind of look through your notes with that to sort of remind yourself of how those laws work, because they will pay off well as we study, functions that do that. Okay, so let's throw down our definition of an exponential function. Okay, so we have that the exponential function with base a, okay, is defined for all real numbers, right, which just means that our domain is all of R, right? For all real numbers, I guess we'll call them X, by f of x equals a to the x, okay? And we say here, where a is greater than 0, well, remember, if a is negative, right, then when we say plug in 1/2 to this, we're going to get something undefined, okay? And we say that a is not equal to 1, right? If a equals 1, then this would just be the constant function 1, and that wouldn't do us very good, okay? So let's look at the graphs of these guys. Let's say graph, we'll do 2 of them. F of x equals 2 to the x, and we'll say g of x equals 1/2 to the x, okay? So we'll fill out a little table of values here. Maybe a little something like that, okay? And I guess we'll go from -3 to 3, because I feel like that will get us a representative sample, okay? Then we can graph those like that. So let's start with f of x first, right? 2 to the -3 is going to be 1/8, right? Because the negative makes it into a reciprocal, right? 2 to the negative 2 is going to be 1 over 4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. Okay? But curiously, notice what happens for g of x, right? When we plug in 3, here we're going to get 1 over 8. When we plug in 2, we're going to get 1 over 4. Plug in 1, we'll get 1/2. Anything to the 0 is 1, okay? What happens when we plug in negative 1 to this? Well, we're going to take the reciprocal. So that means we're going to get 2. When we plug in negative 2, we're going to take the reciprocal and square it. So we're going to get 4. And then same thing here, when we take the reciprocal and cube it, we get 8. So while f sort of runs this way, g runs this way, right? So what happens when we graph this, right? We'll start by putting that actually on the dots, okay? Let's start with f of x, right? At 0, we're at 1. At 1, we're at 2. 2, it looks like we're at 4. And 3, we're at 5, 6, 7, 8, okay? And then it looks like at negative 1, we're at a half. Negative 2, we're at a fourth. Negative third, we're at an 8, right? So it would look to me like f of x is going to have this graph right there, okay? Now what about g of x? Well, we know that 1, 1 is there, and we know that essentially g is a reflection across this axis, right? Because at 1, we're at a half, at 2, we're at a fourth, at 3, we're at an eighth, and so on. And at negative 1, we're at 2. Negative 2, we're at negative 4. Negative 3, we're at 8, right? And so we get the graph of g of x to look a little something like this, okay? And think about why this is, right? Let's take our g of x, which is 1/2 to the x, right? Which if we distribute in that x, that's 1 over 2 to the x, which is 2 to the negative x, right? Which is f of negative x. And if you remember our function transformation, doing a negative x like this flips us over the horizontal axis like that, okay? And so with that specific case under our belt, let's sort of look at the general behavior of these graphs of exponentials, okay? So we can say that the exponential, say f of x equals a to the x, given our restrictions, right? Should be parentheses. It's going to have domain R, right? That's what we said when, I mean, you can look at the graph here, right? This is clearly defined for all real numbers, okay? And it's going to have range 0 to infinity, right? We're never going to quite reach the x-axis here. It's always just going to get closer and closer and closer. It's a horizontal asymptote, right? Let's write that down. The line y equals 0 is a horizontal asymptote, okay? And we can say that the graphs are as follows, okay? So I'll break this up into two cases. have that be one of them, and we'll paste our axes right there for the second. Okay, let's look at what happens when a is greater than 1, right? That looks like what we saw before, right? Remember that anything to the 0 is 1, right? So that means 0, 1's always going to be a point on a graph. And anything to the first power is that number, right? So we're always going to have 0, 1 on our graph, and we're always going to have 1 comma a on our graph, right? And so our function's going to look something like that, right? We're going to have a horizontal asymptote going this way and explode very quickly going that way, right? Tells a very similar story if a is between 0 and 1, right? Anything to the 0 is still 1. So we have 0 comma 1 is on our graph. Anything to the first power is still that original number, right? So 1, so a to the 1 is still a, right? But remember, a is now less than 1. So this is 1 comma a. But if we go the other way, right, negative 1, a to the negative 1 is going to be 1 over a. And because a is in here, that means that 1 over a is going to be larger than 1, right? So we can also get the point, say here, of negative 1 comma 1 over a. And once again, we connect this with our smooth curve and a horizontal asymptote. Okay. So these are our two sort of parent graphs, right? And we can actually use them to our advantage to find equations for graphs, okay? So let's do an example of this, okay? Let's say what is the equation for the given graph of f of x equals a to the x, right? Can we find a value for a? Okay. So we'll start with one of these smaller graphs, okay? We'll do two of these. Let's say we have 1, 1, and I don't know, let's say this is the point 225, right? Those are the only two pieces of information we have. It's just like that, okay? But notice, right? Notice that we have f of 2 equals 25. So now the question is, what do I need to square to get 25, right? But 5 squared equals 25, so a must equal 5, right? So this graph has equation f of x equals 5 to the x, okay? We can do something similar, you know, with a graph that maybe goes the other way, okay? Let's say it has a graph something like this. Right? We still have our 0, 1 here, because unless you do something else to your exponential, it's always going to have 0, 1, and then maybe we have 3 comma 1/8. Okay. So now the question is we notice, right, that f of 3 is 1 over 8. So what do I need to cube in order to get 1 over 8, right? We have a cubed equals 1 over 8, which means a is the cube root of that, right? Or a equals 1/2, right? So that means, so we have g of x, I guess let's call this guy g of x, equals 1 over 2 to the x, right? Or if you prefer to write it this way, 2 to the negative x. And if you recall, right, these ideas of function transformations that we looked at a bit ago that keep coming up, we can totally apply that here too, right? we can say graph the following. And state the domain and range. Okay. We can maybe start with, say g of x is 1 plus 2 to the x. Well, what that's going to do is it's going to take our graph and it's going to shift it up a unit, right? We'll do our parent graphs in red. 1, 2, and I guess we'll go here for 4. Right, and we have this horizontal asymptote here, right? Well, the moment that we shift this up 1 unit, well, each of our points moves up 1 unit, right? Along with our horizontal asymptote moves up 1 unit as well. And so this is what our graph becomes, right? This is g of x. For our domain, we're still going to be all real numbers, right? We haven't changed anything like that. But our range now shifts up 1 unit from 1 to infinity, right? We'll do one more of these, okay? So let's say, h of x is 2 to the x minus 1. We'll need a set of axes, so let's grab these. And then if we erase this, fill in this detail, right? We still keep our parent graph, right? But here's what's happening, right? If we say that f of x equals 2 to the x, then h of x is f of x minus 1, right? So that means that what we're doing is we're shifting our whole graph to the left. It's fairly simple, right? Because we just take each of these points and move them 1 unit here to the left, and we get a little something like that, right? This is h of x, okay? Our domain, once again, is all of R, and our range, well, what's our range going to be? Here we were hitting, for our red graph, right, we were hitting everything that's positive but not 0, right, because this tail is never going to hit 0. And here, on our green graph, we actually have the same situation, right? We're still hitting all of our positive things and never quite reaching 0. So our range is still 0 to infinity. All right, so our next thing to sort of talk and think about is the idea of compound interest, okay? Compound interest is one of these ideas where the tools that we build up to study exponential functions like show up right in your face in everyday life, okay? So say you're investing in something, right? You're going to put in some principal amount, and then after that year, you're going to get, if you have this guaranteed interest rate, right, you're going to get that interest rate times your principal amount back, right? So let's sort of write this out, okay? So at 1 year, you have your principal plus your principal times your interest, right? Where I is your interest rate per year. And if we factor out this p, we get p times 1 plus I. Okay. But here's my question for you, right? What happens if instead of pocketing this, you reinvest the whole thing, right? Well, after 2 years, right, you have your amount you invested plus the amount you invested times your interest, right? And if we factor out this p, right, we're going to get p times 1 plus I plus I squared, right? Where this I is not the imaginary number, right? So we're not doing any sort of I squared equals -1. But if you notice, right, this is the formula for the square of I plus 1, right? So you get p times 1 plus I squared, right? After 3 years, you have 1 plus I cubed. After 4 years, you have 1 plus I to the 4th. And you can show that after, say, k years, right, the amount that you have, right, is p times 1 plus I to the k, right? This right here, this is an exponential, right? So maybe it bears a little bit of study for how this compound interest works, because if we can use the tools that we've developed for this, well, then good on us, right? We're able to understand the investments we're making a little bit better. So that's sort of why we want to study this idea of compound interest, especially in this section, because it's directly applicable to investing things, and also it will give us a sort of real life application to work through these ideas. Okay, so to formalize this definition, okay, we can say that compound interest is calculated by, and here's how it's calculated. Okay, so a of t is our function, okay, where like a is our amount, right? We have our principal p times 1 plus we say r over n over nt, okay? That's a little bit confusing. It's a little different than how we wrote it, but let's define these things, right? We say where a of t is the amount after t years, p is the principal, okay? R is the interest rate per year, okay? N is the number of times compounded per year, and T is the number of years, okay? Right, so like, here our example is compounded yearly, okay? So I know this is a little bit confusing, so let's do an example. So it says you invest $1,000 at an interest rate of 12%, and then we want to find your total after 3 years if interest is compounded annually, quarterly, monthly, and daily, okay? So let's write out these different situations. We have annually, quarterly, monthly, and daily, okay? And if you recall in our formula, there was this n, right? That's the number of times compounded per year. And so let's fill it out for these, right? Well, if we compound annually, we should compound once per year. Quarterly is compounding 4 times per year. Monthly would be compounding 12 times per year, and daily 365. Okay, so now let's plug this into our formula. Okay, for annual, our principal is 1,000. We go 1 plus our interest rate, 0.12, over the number of times we compound per year, times the number of times we compound per year, times the number of years. Okay, when you plug that into your calculator, you're going to get $1,404.93 or so. Okay, what happens if I compound quarterly? Well, we're still going to get 1,000 times 1 plus we have the same interest rate, but now we compound 4 times per year. Okay, so it's a smaller number on input, right? But we're raising it to a higher power because we go 4 times 3, right? And it turns out, when you run this through, you get $1,425.76. Well, that seems great, right? Let's compound monthly, right? Let's see how much more we can make, because we made almost $20 more here by simply compounding more often. We go 1,000 times 1 plus 0.12 over now 12. And we're going to raise it to the 12 times 3, okay? When you run that through, you get $1,430 and around 77 cents. So we made $5 more. Okay, well, we made $5 extra going from 4 to 12. So we should definitely make a ton of money going from 12 to 365, right? So we're going to do 1,000 times 1 plus 0.2 over 365, right? Times 365 times 3. And when you run that through, you get $1,433.24. So somehow this process is slowly approaching a number, okay? And we'll figure out a little bit more about what that means a little bit later, so hang on for that. I do have one more example for you like this. Okay, we're being asked to find the annual yield for an investment that earns an interest rate of 6% annually, but is compounded daily. Okay, and the annual yield here, what that's asking is like, okay, so you have this big fancy interest rate at 6% annually, but it's compounded daily, right? And as we saw right here, when you compound daily, you make more money than if you compound annually. So the annual yield is asking you for the effective rate, right, of compounding daily versus an annual one, okay? And here's how we can calculate that, right? We have our, principal, whatever it is, right? That's going to be multiplied by 1 plus my interest rate of 0.06 over 365, right? And let's say we do this for a year, right? Because we're looking at the annual yield. So that's to the 365. If I plug this into a calculator, right? Well, then that's going to equal P times 1.06183 or so, okay? But if we're looking for the annual yield, right? Well, we're looking for something that looks like P times 1 plus R. So if we put these two pieces of information together, we're going to get that 1 plus R is about, right, 1.0618, okay? Which means if I subtract 1 from both sides, my rate is 0.0618 or 6.18%, right? So for an investment that returns 6% annually, if I compound daily, there's an annual yield, or rather an effective annual interest rate of 6.18%. Now that we've sort of developed these ideas of exponential functions and these common exponential functions, we're going to talk about what is possibly the most important exponential function, okay? And that's the natural exponential, okay? Or the number, as you'll see it called often, the number e, okay? And so the first question is, what is it, right? What is e, okay? And there's a number of different ways to define it. But here's how we're going to define it, okay? We're going to say that e is equal to 1 plus 1 over n to the n as n gets large, very large, okay? And in calculus, right, you will sort of firm up what it means for something like this to equal this expression as n gets very large, okay? But we can sort of use some calculators, right, and kind of get an idea for what it should be, okay? Let's just make a little table, right, of our value of n, n1 plus 1 over n to the n, okay? If n is 1, right, we get 1 plus 1 for 2 to the 1 is 2, okay? So we plug in 10, right? Well, we're going to get about 2.593 or so, right? These are all fairly rounded. We plug in 1,000, right? Multiply by 10 again, we're going to get 2.71692 and so on, okay? What if we plug in something huge, right? Like a million, okay? Well, if we do that, we're going to get about 2.71828 and on and on and on, okay? And it turns actually out a million is actually enough to get us the first 6 digits, okay? E is approximately 2.718 2818, and on and on and on and on, okay? For our sake, most of the time, knowing that e is 2.718 is good enough, okay? And also with almost all of the calculations we'll be doing with the natural exponential and the natural exponent, we'll just be leaving it in exact form, and you won't need to simplify it or put it in a calculator or anything like that, okay? So with this behind us, okay, let's write down this formal definition, right? The natural exponential I guess this is the natural exponential function, okay? It's the function f of x equals e to the x, okay, where our base is e, and also you will sometimes hear people refer to this, right, as this is the exponential function, right? And the reasoning behind that is sort of beyond the scope of this class. If you take calculus, you'll sort of get some intuition for that. There, it's actually very interesting, okay? Looking at these graphs, okay, I guess we're just graphing. I guess we're doing this in red, okay? So we know that our base is going to be, you know, about 2.718, which means we're going to lie between the graph of 2 to the x and the graph of 3 to the x. But we're going to look a little something like this, right? At 0, we're at 1. At 1, we're at e, right? So that's going to be the 2.7, okay? At 2, we're going to be at that squared. But it's sufficient to say that it's going to zoom off very high, right? Similarly, at -1, we have 1 over e. We'll just call that guy here, right? One of the side effects of exponentials all looking so similar, right, is that it can sometimes be hard to tell which one you're graphing, right? That's why it's always important to label some of your points on it, and often even just label your graph, okay? If you're graphing e to the negative x, Well, it would do the same thing. It would just flip around the y-axis, okay, for something like that, okay? Nice and simple. But where these ideas of the natural exponential really come to fruition, right, is actually with a thing called continually compounded interest, okay? And here's what's continually compounded interest is all about, okay? It asks the same question, okay? So if we recall that we have this a of t, this p times 1 plus r over n to the nt, okay? So what happens as n goes to infinity, right? What happens if we, rather than compound, daily, we compound hourly or minutely or every second or every instant? We're always compounding, okay? So this is how we're going to do it, right? We're going to take our function, a of t is 1 plus r over n to the nt, and we're going to make a little clever substitution, okay? So let's say m, right, some variable m, is equal to n over r, right? And the note, as n goes to infinity, m is going to go to infinity, right? Because my rate is fixed, right? So let's see what happens there. We have p times 1 plus, well, if m is n over r, then r over n is 1 over m, okay? And we're going to take this nt, and we're going to do another little sneaky trick. We're going to multiply by r over r, okay? So what's that going to do? Well, that's going to be 1 plus 1 over m. We're going to get n over r times rt. But n over r is m. So we have p times 1 plus 1 over m to the m, and all of that is to the rt, right? But remember, right, we're looking as n is going to infinity, which means m is going to infinity, right? And what happens is this expression for this value of m goes to infinity. Well, that's the definition of E, right? So then we get this formula. It's often called the PERT formula, right? Where it tells us our output, right? When we invest some principal, right, at some interest rate for some number of years, right? This is how you get your continually compounded interest. You're not worrying about, this r over n to the nt or anything. It's just my principal times the natural exponential raised to this specific power. And so I have one last example for you. Okay, so we're being asked to find the amount, right, after 3 years if you invest $1,000 at 12% compounded continuously. Okay, so we have our function a of t, and a of t, well, that's equal pe to the rt. Filling in, we have a principal of $1,000. E, my rate is 0.12, and my time is 3 years. Okay, if we plug this into a calculator, right, we have 1,000 times e to the 0.36, right? We're going to get $1,433.33. Okay, if you compare that to what we did in the last little section, daily got you $1,433.24. So compounding continuously, it earns you an extra 9 cents over the course of the year. But hey, those 9 cents will add up a lot over time if you're always continuously compounding. Okay. So that's going to wrap it up for this week. Next week, we're going to keep doing our study of these exponentials and logarithms. And so I'll see you then.